Picture this, you're sitting in the most advanced spacecraft humanity has ever built. The engines roar to life and you feel the incredible force pushing you back into your seat. You're accelerating faster than any human has ever traveled before. The Earth shrinks behind you, the solar system becomes a distant memory, and you're racing toward the stars at unimaginable speeds. But here's the thing that might shock you. No matter how powerful your engines are, no matter how much energy you pump into them, you will never, ever reach the speed of light. This isn't just a limitation of our current technology. This isn't something we'll overcome in 100 years or 1,000 years. The universe itself has written laws that make light speed travel impossible for anything with mass. And today, we're going to explore exactly why Einstein's cosmic speed limit isn't just a suggestion. It's an absolute barrier that governs everything in our universe. If you're curious about these cosmic mysteries, make sure to subscribe to this channel and give a thumbs up. Your support means a lot to me. One quick question. If you could travel at 99% the speed of light, where in the universe would you go first? Let me know in the comments below. I will choose the most creative answer. Now let's begin. You might think that reaching light speed is just an engineering problem. After all, we've gone from horse-drawn carriages to rockets that can escape Earth's gravity in just over a century. Surely with enough time and technology, we can build something fast enough to match light itself, right? Wrong. And the reasons why will fundamentally change how you think about space, time, energy, and the very fabric of reality. The speed of light, approximately 299,792,458 meters per second, isn't just fast. It's the cosmic speed limit that Einstein discovered governs our entire universe. But why this specific number? Why can't we go faster? And what happens when we try? But this isn't just about limitations. Understanding why we can't reach light speed reveals some of the most beautiful and mind-bending truths about our universe. It shows us how space and time are woven together, how energy and matter dance in cosmic harmony, and why the speed of light is so much more than just a number. It's the heartbeat of reality itself. If you're fascinated by how we discovered the speed of light and how it became the universe's ultimate speed limit, I highly recommend the book Measuring the Universe, The Historical Quest to Quantify Space by Kitty Ferguson. It's a captivating journey through the experiments, breakthroughs, and brilliant minds that revealed the true nature of light speed and changed our understanding of reality. You'll find the link in the description. Think about the fastest things you know. A cheetah running at 70 miles per hour seems incredibly fast until you compare it to a jet flying at 600 miles per hour. That jet seems lightning quick until you consider a rocket escaping Earth at 25,000 miles per hour. But even our fastest spacecraft are crawling compared to light. The Voyager 1 probe, humanity's fastest and most distant ambassador, has been traveling for over 45 years and has only reached about 38,000 miles per hour. At that speed, it would take over 70,000 years to reach our nearest star neighbor, Proxima Centauri. Light makes that same journey in just over 4 years. That's the difference we're talking about, not just faster, but incomprehensibly, impossibly faster. And yet, despite this incredible speed, light itself reveals why nothing with mass can ever match its pace. The story begins with a young patent clerk in Switzerland who dared to ask a simple question. What would it be like to ride alongside a beam of light? Albert Einstein's thought experiment in 1905 didn't just change physics, it revealed that our intuitive understanding of speed, time, and space was completely wrong. Before Einstein, we thought of space and time as separate, absolute things. Space was like a giant stage where events happened, and time was like a universal clock ticking the same for everyone, everywhere. If you were on a train moving at 50 miles per hour and threw a ball forward at 20 miles per hour, someone standing on the platform would see that ball moving at 70 miles per hour. Simple addition, right? But light doesn't follow these rules. No matter how fast you're moving when you measure light's speed, you always get the same answer, approximately 300 million meters per second. This seems impossible, but it's been confirmed in countless experiments. Whether you're standing still, flying in a jet, or zooming through space in a rocket, light always passes you at exactly the same speed. This discovery forced Einstein to a shocking conclusion. Space and time aren't separate at all. They're woven together into something called space-time, and this fabric can stretch and compress depending on how fast you're moving. As you approach the speed of light, time itself slows down for you, and space contracts in the direction you're traveling. The universe literally reshapes itself to ensure that light always maintains its cosmic speed limit. But here's where things get really interesting and really impossible for massive objects like us. As you accelerate toward light speed, something called relativistic mass increase kicks in. The faster you go, the more massive you become from the perspective of someone watching you. And as your mass increases, it takes more and more energy to accelerate you further. This isn't just a small effect. When you're traveling at 90% the speed of light, your relativistic mass has increased by about 2.25 times. At 99% light speed, you're over 7 times more massive. At 99.9%, you're over 22 times more massive. And as you get closer and closer to light speed, your mass approaches infinity. Think about what this means. To accelerate an object with infinite mass would require infinite energy. And since there isn't infinite energy available in the universe, reaching light speed becomes not just difficult, but mathematically impossible. The universe has built in its own protection system, ensuring that the cosmic speed limit can never be broken by anything with mass. This is where many people ask, but what about photons? How do they travel at light speed if nothing with mass can reach that speed? The answer is beautifully simple. Photons have no mass at all. They don't accelerate to light speed. They're created already traveling at light speed, and they can never slow down. For a photon, light speed isn't a destination. It's the only speed that exists. This reveals something profound about our universe. The speed of light isn't really about light at all. It's the speed of causality itself, the maximum rate at which cause and effect can propagate through space-time. Light just happens to travel at this fundamental speed because it has no mass to slow it down. But the impossibility of reaching light speed goes even deeper than mass and energy. It touches the very nature of time itself, and this is where things get truly mind-bending. Now let's dive into perhaps the most famous equation in all of science, E equals mc squared. Most people know this equation, but few truly understand how it creates an absolutely insurmountable barrier to light speed travel. This isn't just about energy and mass, it's about the fundamental structure of reality itself. When Einstein derived this equation in 1905, he revealed something shocking. Mass and energy are not separate things. They're different forms of the same fundamental quantity. Mass is simply concentrated energy, and energy can be converted into mass. This discovery didn't just change physics, it revealed why the universe has built-in protection against faster-than-light travel. Let's start with what this equation actually tells us. The E represents energy, m represents mass, and c represents the speed of light. But here's the crucial part. C is squared, meaning it's multiplied by itself. The speed of light is approximately 300 million meters per second, so c squared is about 9 times 10 to the 16th meters squared per second squared. That's a monumentally large number. What this means is that even a tiny amount of mass contains an enormous amount of energy. A single paperclip weighing about 1 gram contains enough energy to power a city of 100,000 people for an entire day. That energy is locked up in the mass itself, bound together by the fundamental forces that hold matter together. But here's where things get interesting for our light speed problem. As you accelerate any object with mass, you're not just making it move faster, you're actually adding energy to it. And according to E equals mc squared, adding energy means adding mass. The faster you go, the more energy you have and the more massive you become. This creates what physicists call relativistic mass increase. It's not that new matter is being created, rather, the energy you're pumping into the object to make it go faster is manifesting as additional mass. And this additional mass makes it even harder to accelerate the object further. Think of it like trying to fill a bucket that gets bigger every time you pour water into it. The more water you add, the larger the bucket becomes, requiring even more water to fill it. Similarly, the more energy you add to accelerate an object, the more massive it becomes, requiring even more energy to accelerate it further. At everyday speeds, this effect is negligible. When you're driving your car at 60 miles per hour, your relativistic mass increase is so tiny that it's completely undetectable. But as you approach significant fractions of light speed, this effect becomes dramatic and eventually catastrophic. Let's put some real numbers to this cosmic impossibility. Imagine we want to accelerate the International Space Station, which weighs about 420 tons, to various fractions of light speed. At 10% light speed, the energy required would be equivalent to the total energy output of the Sun for about 3 seconds. That's already an impossible amount of energy for any conceivable technology. At 50% light speed, we'd need energy equivalent to the Sun's total output for about 45 minutes. At 90% light speed, we're looking at over 5 hours of the Sun's total energy output. And remember, this is just to reach 90%. We're not even close to light speed yet. At 99% light speed, the energy requirement jumps to about 36 hours of the Sun's total output. At 99.9%, we need over 11 days. At 99.99%, we're looking at over 100 days of the Sun's complete energy output just to accelerate one space station. And here's the kicker. To reach exactly 100% light speed would require infinite energy. Not just a lot of energy, not just more energy than exists in our solar system or galaxy, but literally infinite energy. Since the universe contains only finite energy, this makes light speed travel mathematically impossible. But the universe has even more barriers in store for us. Let's talk about what happens to the very atoms that make up your body as you approach light speed. Every atom in your body is held together by electromagnetic forces. These forces have a finite strength, and as you accelerate to extreme speeds, the stresses on your atomic structure become enormous. At very high speeds, the electromagnetic forces that hold your atoms together would begin to struggle against the relativistic effects. Your body would experience what physicists call relativistic stress. The front of your body would experience different forces than the back, potentially tearing you apart at the atomic level long before you could reach light speed. Even if we could somehow overcome the energy requirements, even if we could gather infinite energy from somewhere, the very matter we're trying to accelerate would disintegrate under the extreme conditions. The universe seems to have multiple backup systems to ensure that its cosmic speed limit is never violated. This brings us to another fascinating aspect of the light speed barrier. It's not just about individual objects, but about information itself. In our universe, information cannot travel faster than light. This isn't just a technological limitation, it's a fundamental feature of space-time that preserves causality. If information could travel faster than light, it could theoretically arrive before it was sent, creating paradoxes that would undermine the logical structure of reality. The speed of light barrier ensures that cause always precedes effect, maintaining the rational order of the universe. Consider what this means for any hypothetical faster-than-light communication or travel. Even if we could somehow bypass the energy requirements and structural limitations, we'd be violating the fundamental principle that information cannot travel faster than light. We'd be breaking not just the laws of physics, but the logical consistency of reality itself. But here's something beautiful about these limitations. They reveal the elegant interconnectedness of our universe. The same constant that determines the speed of light also appears in equations describing electromagnetic forces, quantum mechanics, and the structure of space-time itself. The speed of light isn't just a speed, it's a fundamental constant that weaves together all the forces and phenomena in our universe. This constant, often represented by the letter C, appears in dozens of fundamental equations. It determines how electric and magnetic fields relate to each other, how energy and momentum are connected, and how space and time are unified. It's the cosmic thread that holds the fabric of reality together. The impossibility of reaching light speed also reveals something profound about the nature of mass itself. Photons, the particles of light, have zero mass. This isn't just a small amount of mass, it's exactly zero. And because they have no mass, they don't experience the relativistic effects that prevent massive objects from reaching light speed. For a photon, light speed isn't a destination to reach, it's the only speed that exists. Photons are created already traveling at light speed, and they can never slow down or speed up. They exist in a realm where time doesn't pass and distance doesn't exist in the way we understand it. This creates a beautiful symmetry in the universe. Massless particles must travel at light speed, while massive particles can never reach it. The speed of light serves as a perfect dividing line between two fundamentally different types of existence. The realm of mass, where time passes and distance matters, and the realm of pure energy, where time stands still and space contracts to nothing. Understanding this barrier also helps us appreciate why the universe is structured the way it is. If massive objects could travel at light speed, the distinction between matter and energy would break down. The careful balance of forces that allows stars to shine, planets to orbit, and life to exist would be disrupted. The light speed barrier isn't a limitation, it's a feature. It's what allows our universe to have stable structures, predictable physics, and the kind of ordered complexity that makes life possible. Without this cosmic speed limit, the universe would be a chaotic place where cause and effect could be scrambled, where energy and matter could interchange freely, and where the stable structures we depend on could not exist. To truly understand why we can never reach the speed of light, we need to dive into the quantum realm, the strange, counterintuitive world of the very small, where particles behave in ways that challenge our everyday understanding of reality. Here, we'll discover that the speed of light isn't just a cosmic speed limit, it's woven into the very fabric of existence at the most fundamental level. In the quantum world, light reveals its true nature as both wave and particle. This isn't just a metaphor. Light literally exhibits both properties depending on how we observe it. When we're not looking, light behaves like a wave, spreading out and interfering with itself. But the moment we try to detect it, it behaves like a particle, appearing at specific locations with definite energies. This wave-particle duality is crucial to understanding why light speed is so special. As a wave, light is an oscillation in the electromagnetic field that permeates all of space. This field is one of the fundamental fields of nature, and its oscillations naturally propagate at exactly the speed of light. It's not that light chooses to travel at this speed, it's that electromagnetic waves can only exist at this speed. But here's where quantum mechanics reveals something even more profound. The speed of light emerges from two fundamental constants of nature, the electric permittivity and magnetic permeability of free space. These aren't arbitrary numbers, they're built into the structure of space-time itself. The speed of light is literally the speed at which changes in electric and magnetic fields can propagate through the vacuum of space. This means that the speed of light is fundamentally connected to the structure of empty space itself. Even in a perfect vacuum, space isn't truly empty. It's filled with quantum fields that are constantly fluctuating at the smallest scales. These quantum fluctuations create what physicists call the zero-point energy of the vacuum, and they establish the fundamental properties that determine light speed. When we try to accelerate massive particles to light speed, we're not just fighting against energy requirements, we're fighting against the quantum structure of space-time itself. Every massive particle is constantly interacting with these quantum fields, and these interactions become more and more intense as we approach light speed. Let's explore what happens to matter at the quantum level as it approaches these extreme speeds. Every atom in your body contains electrons orbiting around a nucleus. These electrons are held in their orbits by electromagnetic forces, and they exist in specific quantum energy levels. As you accelerate to high speeds, the relativistic effects begin to distort these quantum energy levels. At 90% light speed, the quantum mechanical properties of atoms begin to change dramatically. The electron orbitals become distorted, and the energy levels shift in ways that would fundamentally alter the chemical properties of matter. At 99% light speed, these effects become so extreme that normal atomic structure begins to break down. But the quantum world reveals an even deeper barrier. According to quantum field theory, every particle with mass is actually an excitation in a quantum field that permeates all of space. Electrons are excitations in the electron field, protons are excitations in the quark fields, and so on. These field excitations have a natural rest mass that determines their behavior. When we try to accelerate these field excitations to light speed, we're asking them to behave in a way that's fundamentally incompatible with their nature. Massive field excitations simply cannot exist at light speed. It would violate the mathematical structure of quantum field theory itself. Photons, on the other hand, are excitations in the electromagnetic field, which is a massless field. These excitations naturally propagate at light speed because that's the only speed at which massless field excitations can exist. For photons, traveling at light speed isn't a choice, it's a fundamental requirement of their existence. This reveals something beautiful about the structure of our universe. The speed of light isn't really about light at all, it's about the fundamental speed at which massless information can propagate through space-time. Light just happens to be massless, so it travels at this fundamental speed. But this speed is built into the very structure of reality at the quantum level. The quantum world also reveals why the energy requirements for reaching light speed become infinite. In quantum mechanics, energy and momentum are related through Einstein's energy-momentum relation. E squared equals pc squared plus mc squared squared, where p is momentum, m is rest mass, and c is the speed of light. For a massive particle, as its momentum approaches infinity, which is what would be required to reach light speed, its energy also approaches infinity. But here's the crucial point. In quantum mechanics, infinite energy would mean infinite mass, and infinite mass would create a black hole. The universe literally prevents light speed travel by threatening to collapse any object that tries into a gravitational singularity. But quantum mechanics offers us another perspective on why light speed is special. According to the uncertainty principle, there are fundamental limits to how precisely we can know certain pairs of properties simultaneously. The more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. For a particle traveling at light speed, This uncertainty principle creates a paradox. To travel at exactly light speed, a massive particle would need to have precisely defined momentum. But the uncertainty principle tells us that this would make its position completely undefined. It would be spread out across all of space simultaneously. A massive particle simply cannot exist in such a state. Photons avoid this paradox because they're massless. For massless particles, the uncertainty principle allows them to have well-defined momentum while still maintaining a coherent existence. This is yet another way that the universe ensures only massless particles can travel at light speed. The quantum world also reveals the deep connection between light speed and the structure of space-time itself. In quantum field theory, space-time isn't a smooth, continuous fabric. It's a seething foam of quantum fluctuations at the smallest scales. These fluctuations occur at the Planck scale, where distances are about 10 to the minus 35 meters and times are about 10 to the minus 43 seconds. At these incredibly tiny scales, the very concepts of space and time begin to break down. But even here, the speed of light emerges as a fundamental constant that governs how these quantum fluctuations propagate. The speed of light is literally built into the quantum structure of space-time itself. This quantum foam also creates what physicists call vacuum resistance. As particles move through space, they're constantly interacting with these quantum fluctuations. For massive particles approaching light speed, these interactions become so intense that they create an effective resistance that prevents further acceleration. It's like trying to move through an increasingly thick fluid. The faster you go, the thicker the quantum foam becomes, until it becomes impossible to push through. This isn't just a metaphor. The mathematics of quantum field theory shows that vacuum resistance becomes infinite as massive particles approach light speed. But perhaps the most profound insight from quantum mechanics is that the speed of light represents the speed of causality itself. In the quantum world, cause and effect are mediated by the exchange of virtual particles. These virtual particles carry information about forces and interactions, and they can only propagate at the speed of light, or slower. This means that the speed of light isn't just a speed limit for matter and energy, it's a speed limit for cause and effect themselves. If anything could travel faster than light, it could potentially disrupt the causal structure of space-time, creating paradoxes that would undermine the logical consistency of the universe. But what if we could travel faster than light? If you are interested, I talk about that in my video called "What Would Happen If We Could Travel Faster Than Light?" In this video, discover the mind-blowing science and consequences of breaking the cosmic speed limit. Explore how faster-than-light travel would transform space exploration, time, and the future of humanity. Check it out after watching this video. The link is in the description and on the card above. Now let's continue. The quantum world shows us that the speed of light barrier isn't just about energy or mass. It's about preserving the fundamental structure of reality itself. Every quantum field, every particle interaction, every force in nature respects this cosmic speed limit because it's built into the very foundation of existence. Understanding these quantum mechanical barriers helps us appreciate why the speed of light is so much more than just a number. It's a fundamental constant that emerges from the deepest levels of reality, connecting the behavior of subatomic particles to the large-scale structure of space-time itself. The theoretical barriers to light-speed travel might seem abstract, but the universe has provided us with countless real-world experiments and observations that confirm these limitations with stunning precision. From particle accelerators buried beneath the Swiss countryside to cosmic ray detectors scattered across the globe, every piece of experimental evidence points to the same inescapable conclusion. The speed of light is truly the ultimate cosmic speed limit. Let's start with the most powerful machines humanity has ever built, particle accelerators. The Large Hadron Collider, stretching 27 kilometers beneath the border of France and Switzerland, routinely accelerates protons to 99.99991% the speed of light. That's incredibly close. So close that these protons are moving only about 3 meters per second slower than light itself. But here's the remarkable thing. Despite pumping enormous amounts of energy into these protons, scientists have never been able to push them that final tiny bit to reach actual light speed. The energy requirements grow exponentially as they approach this barrier, exactly as Einstein's equations predict. Each additional decimal place of precision toward light speed requires roughly 10 times more energy than the previous decimal place. To put this in perspective, the LHC uses about 120 megawatts of power when running at full capacity, enough to power a small city. All of this energy goes into accelerating tiny subatomic particles that weigh less than a trillionth of a gram. And yet, even with this enormous energy expenditure, the particles never quite reach light speed. The Tevatron accelerator at Fermilab, which operated from 1983 to 2011, provided decades of data confirming these relativistic effects. Scientists could measure the increasing mass of particles as they approached light speed, watching Einstein's predictions play out with mathematical precision. The faster the particles went, the more massive they became, requiring ever-increasing amounts of energy for further acceleration. But particle accelerators aren't the only evidence. Nature provides its own cosmic accelerators that dwarf anything humans have built. Cosmic rays, high-energy particles from deep space, regularly strike Earth's atmosphere with energies that make our most powerful accelerators look like toys. Some cosmic ray particles carry energies equivalent to a baseball traveling at 60 miles per hour, all concentrated in a single subatomic particle. These ultra-high-energy cosmic rays have been accelerated by some of the most violent processes in the universe: supernova explosions, black hole jets, and colliding neutron stars. They've been traveling through space for millions or billions of years, gaining energy from magnetic fields and shock waves that span entire galaxies. And yet, even these cosmically accelerated particles never exceed the speed of light. The Pierre Auger Observatory in Argentina, covering an area larger than Rhode Island, detects these cosmic ray particles when they slam into Earth's atmosphere. The observatory has recorded particles with energies over 10 to the 20th electron volts, energies so high that they approach the theoretical maximum possible in our universe. But even these incredibly energetic particles obey Einstein's speed limit. When these cosmic ray particles hit our atmosphere, they create cascades of secondary particles that rain down across hundreds of square kilometers. By studying these particle showers, scientists can reconstruct the energy and speed of the original cosmic ray. In every case, without exception, the particles are traveling at less than light speed, no matter how much energy they carry. The Global Positioning System provides another everyday confirmation of relativistic effects. GPS satellites orbit Earth at about 14,000 kilometers per hour, fast enough that relativistic time dilation becomes measurable. The atomic clocks on these satellites run slightly faster than identical clocks on Earth's surface, gaining about 38 microseconds per day due to relativistic effects. This might seem like a tiny amount, but it's enough to throw off GPS calculations by several kilometers, if not corrected. The fact that your smartphone can pinpoint your location to within a few meters is direct proof that Einstein's theories are correct. Every time you use GPS navigation, you're relying on corrections for relativistic effects that become more extreme as speeds approach light speed. Muons created in Earth's upper atmosphere provide another beautiful confirmation of time dilation. These particles are created when cosmic rays collide with atmospheric molecules about 15 kilometers above the surface. Muons are unstable and decay with a half-life of only 2.2 microseconds. At this rate, they should all decay long before reaching the ground, even traveling at near-light speeds. But muons do reach the ground, and we can detect them in laboratories around the world. The reason is time dilation. From our perspective, the muons are traveling so fast that time slows down for them, allowing them to survive much longer than their normal lifetime. This effect has been measured countless times and always matches Einstein's predictions exactly. The Michelson-Morley experiment, first performed in 1887 and repeated with increasing precision ever since, provides fundamental evidence for the constancy of light speed. This experiment was designed to detect Earth's motion through what 19th century physicists thought was a medium called the luminiferous ether that carried light waves. The experiment used an interferometer to compare the speed of light in different directions as Earth moved through space. If light traveled through a medium, its speed should vary depending on Earth's motion through that medium, just as sound travels faster or slower depending on wind direction. But the experiment found no variation whatsoever. Light traveled at exactly the same speed in all directions. This null result was initially puzzling, but it led directly to Einstein's realization that the speed of light is constant for all observers, regardless of their motion. Countless repetitions of this experiment using increasingly sophisticated equipment have confirmed this result to extraordinary precision. Light speed is truly constant, independent of the motion of the source or observer. Modern versions of the Michelson-Morley experiment use laser interferometry and can detect changes in light speed as small as 1 part in 10 to the 17th. The laser interferometer, Gravitational Wave Observatory or LIGO, uses this principle to detect gravitational waves by measuring tiny changes in the distance light travels between mirrors. These experiments continue to confirm that light speed is absolutely constant. Synchrotron radiation provides another compelling piece of evidence. When charged particles are accelerated in circular paths, they emit electromagnetic radiation. The frequency and intensity of this radiation depend on the particle's speed and energy. In particle accelerators around the world, scientists observe this synchrotron radiation and use it to precisely measure particle velocities. As particles approach light speed, the characteristics of their synchrotron radiation change in exactly the ways Einstein's equations predict. The radiation becomes more intense and shifts to higher frequencies, but the particles never quite reach the point where they would be traveling at light speed. The radiation patterns provide a direct window into the relativistic effects that prevent light speed travel. Particle decay experiments offer yet another confirmation. Many subatomic particles are unstable and decay into other particles after a characteristic lifetime. But when these particles are accelerated to high speeds, their lifetimes increase due to time dilation. The faster they go, the longer they live, exactly as relativity predicts. Scientists have measured this effect for dozens of different particle types, from pions and kaons to exotic particles that exist for only tiny fractions of a second. In every case, the lifetime dilation follows Einstein's equations precisely. Particles traveling at 99% light speed live about 7 times longer than particles at rest. The behavior of light itself in different media provides additional evidence for the fundamental nature of the light speed barrier. When light travels through materials like glass or water, it slows down due to interactions with the atoms in the material. But this apparent slowing is actually due to absorption and re-emission processes. The individual photons still travel at light speed between atoms. More importantly, when light emerges from these materials back into vacuum, it immediately returns to its full speed. Light cannot be permanently slowed down or sped up. It always returns to its fundamental speed when traveling through empty space. This behavior is consistent with light speed being a fundamental property of spacetime itself, not just a property of light. Astronomical observations provide evidence on cosmic scales. When we observe distant supernovae, we can measure both the light they emit and the neutrinos they produce. Neutrinos have tiny masses and travel at very close to light speed, but not quite at light speed. Light, being massless, travels at exactly light speed. For supernovae in our own galaxy, the difference in arrival times between light and neutrinos is measurable and matches theoretical predictions. The neutrinos arrive slightly later than they would if they traveled at light speed, confirming that even these nearly massless particles cannot quite reach the cosmic speed limit. To truly grasp why light speed is an absolute barrier, we need to understand that space and time are just a stage where physics happens. They're dynamic, interconnected entities that form the very fabric of reality. This fabric, called space-time, has a geometry that makes light-speed travel for massive objects not just difficult, but geometrically impossible. Imagine space-time as a vast, four-dimensional fabric, where 3 dimensions represent space and 1 represents time. This isn't just a metaphor, it's a mathematical reality that describes how our universe actually works. Every event that has ever happened, from the birth of stars to the collision of subatomic particles, occurs at specific coordinates in this 4-dimensional space-time. Now here's where things get mind-bending. The geometry of space-time isn't flat like a piece of paper. It's curved and warped by the presence of mass and energy. Every object with mass creates a depression in this fabric, and the motion of objects through space-time follows the curves and contours of this geometry. What we experience as gravity is actually the curvature of space-time itself. But the speed of light plays a special role in this geometry. In space-time, there are 3 types of paths that objects can follow: time-like paths, space-like paths, and light-like paths. Massive objects can only follow time-like paths, which always involve moving slower than light. Massless particles like photons follow light-like paths, traveling at exactly light speed. Space-like paths would represent faster than light travel, but they're forbidden for any real object or information. This isn't just a rule imposed on space-time, it's built into the fundamental geometry itself. The mathematical structure of space-time makes space-like paths physically meaningless for massive objects. It would be like trying to travel north of the North Pole. The geometry simply doesn't allow it. To understand this better, let's explore what physicists call the light cone. At every point in space-time, you can imagine a cone extending into the future and another extending into the past. The surface of these cones represents all the paths that light could take from that point. The inside of the future cone represents all the places you could potentially reach, and the inside of the past cone represents all the places that could have influenced you. The crucial point is that massive objects are forever trapped inside these light cones. You can never escape to the outside of the cone, because that would require traveling faster than light. The light cone defines the absolute boundary of what's causally connected to your current location in space-time. This geometric constraint has profound implications. It means that the universe has a built-in structure that prevents paradoxes and maintains causality. If you could travel outside your light cone, you could potentially influence events in your own past, creating logical contradictions that would undermine the rational structure of reality. The geometry of space-time also explains why time dilation and length contraction occur as you approach light speed. As you move faster through space, you're actually rotating your path through 4-dimensional space-time. The faster you move through the spatial dimensions, the slower you move through the time dimension. At light speed, all your motion would be through space, with no motion through time at all. This rotation through space-time is described by what physicists call Lorentz transformations. These mathematical equations show exactly how space and time coordinates change as you move from one reference frame to another. They reveal that space and time are not separate entities, but different aspects of a unified four-dimensional reality. As you approach light speed, these Lorentz transformations become more and more extreme. Time dilation approaches infinity, length contraction approaches zero, and the energy required for further acceleration approaches infinity. These aren't just practical limitations, they're geometric features of space-time itself. The concept of proper time helps illustrate this geometric reality. Proper time is the time measured by a clock that travels with you through space-time. It's the time you actually experience regardless of how fast you're moving. The remarkable thing is that proper time is a geometric invariant. It's the same for all observers, even though they might disagree about coordinate time and distance. As you approach light speed, your proper time begins to diverge dramatically from coordinate time. From the perspective of someone watching you, your clocks slow down and eventually appear to stop. But from your perspective, time continues to flow normally. This isn't just an illusion. It's a real geometric effect of moving through curved space-time. The geometry of space-time also reveals why photons can travel at light speed, while massive particles cannot. Photons follow what are called null geodesics, the straightest possible paths through space-time that have zero proper time. For a photon, the journey from one point to another takes no time at all from its own perspective, regardless of how far it travels. Massive particles, on the other hand, must follow time-like geodesics. These paths always have positive proper time, meaning that some time must always pass for the particle as it moves through space-time. This geometric requirement makes it impossible for massive particles to follow the null geodesics that would correspond to light-speed travel. Einstein's field equations, which describe how mass and energy curve space-time, provide the mathematical foundation for understanding these geometric constraints. These equations show that the presence of mass and energy determines the curvature of space-time, which in turn determines how objects move through it. The solutions to Einstein's field equations reveal many exotic possibilities: black holes where space-time curvature becomes infinite, wormholes that might connect distant regions of space, and even cosmological models where space itself expands faster than light. But in every case, these solutions respect the fundamental constraint that massive objects cannot travel faster than light through space-time. Even in the most extreme environments, near black holes, in the hearts of neutron stars, or during the first moments after the Big Bang, the light-speed barrier remains absolute. Matter can be compressed to incredible densities, accelerated by gravitational fields millions of times stronger than Earth's, and subjected to temperatures of billions of degrees, but it can never be pushed beyond the cosmic speed limit. The geometry of space-time also explains why faster-than-light travel would violate causality. In relativity, events that are simultaneous for one observer may not be simultaneous for another observer moving at a different velocity. This relativity of simultaneity means that if faster-than-light travel were possible, different observers would disagree about the order of cause and effect. Consider a hypothetical faster-than-light message sent from Earth to a distant star. From Earth's perspective, the message is sent first and received later. But from the perspective of an observer moving at high speed relative to Earth, the message might appear to be received before it was sent. This would create a causal paradox that would undermine the logical structure of space-time. The geometric structure of space-time prevents these paradoxes by making faster-than-light travel impossible. The light cones that define causal relationships ensure that cause always precedes effect for all observers, maintaining the rational order of the universe. This geometric understanding also helps explain why the speed of light is the same for all observers. In space-time geometry, the speed of light isn't really a speed at all. It's a conversion factor between space and time coordinates. It's built into the metric of space-time itself, determining how distances and durations are related. Just as the ratio of a circle's circumference to its diameter is always pi regardless of the circle's size, the speed of light is always the same regardless of the observer's motion. It's a fundamental geometric property of the space-time we inhabit. The curvature of space-time near massive objects provides additional evidence for these geometric constraints. Near a black hole, space-time is so severely curved that time dilation becomes extreme. An observer falling toward a black hole would appear to slow down and eventually freeze at the event horizon from the perspective of a distant observer. But even in these extreme conditions, the falling observer never exceeds light speed. The geometry of space-time ensures that no matter how strong the gravitational field, massive objects always remain within their light cones. The event horizon of a black hole represents the boundary where light cones tip over so far that they no longer point away from the black hole, but even here, the light speed limit is preserved. Gravitational waves, ripples in space-time itself, also travel at exactly light speed. When two black holes collide billions of light-years away, the gravitational waves they produce travel through space at light speed, carrying information about the collision. These waves stretch and compress space-time as they pass, but they never exceed the fundamental speed limit built into space-time's geometry. Part 7. Thermodynamics and Information. Theory barriers. The impossibility of reaching light speed isn't just about energy, mass, or space-time geometry. It's also fundamentally connected to the laws of thermodynamics and information theory. These connections reveal that the light speed barrier is woven into the very fabric of how information, energy, and entropy behave in our universe. Let's start with the second law of thermodynamics, which states that entropy, a measure of disorder, always increases in isolated systems. This law has profound implications for light speed travel that most people never consider. Every process that accelerates matter requires the conversion of organized energy into kinetic energy, and this conversion always produces waste heat and increases entropy. As you approach light speed, the energy requirements grow exponentially, but so does the entropy production. The amount of waste heat generated becomes enormous, and this heat must be dissipated somehow. But here's the problem. As you approach light speed, your ability to radiate away this waste heat becomes severely limited by relativistic effects. From the perspective of an outside observer, an object approaching light speed appears to contract in length and slow down in time. This means that the surface area available for heat radiation decreases, while the time available for heat dissipation also decreases. The object becomes trapped in its own waste heat, creating a thermodynamic barrier that prevents further acceleration. This effect becomes catastrophic as you approach light speed. The energy density within the accelerating object grows without bound, while its ability to dissipate that energy approaches zero. Long before you could reach light speed, the object would be destroyed by its own thermal radiation, melting or vaporizing from the inside out. But the thermodynamic barriers go even deeper. Consider what happens to the information content of an object as it approaches light speed. Every atom in your body contains information, the positions and velocities of electrons, the quantum states of nuclei, the complex molecular structures that make life possible. This information must be preserved during acceleration, but relativity places fundamental limits on how much information can be contained in a given volume of space. As an object approaches light speed, length contraction compresses it in the direction of motion. This compression increases the information density, packing more and more data into a smaller and smaller volume. But there's a fundamental limit to how much information can be stored in any given region of space known as the Bekenstein bound. The Bekenstein bound states that the maximum amount of information that can be contained in a spherical region is proportional to the area of the sphere's surface, not its volume. This limit is derived from black hole thermodynamics and represents a fundamental constraint on information storage in our universe. As an object approaches light speed and undergoes length contraction, it eventually reaches a point where its information content would exceed the Bekenstein bound. At this point, the object would be forced to collapse into a black hole to avoid violating this fundamental limit. The universe literally prevents light speed travel by threatening to turn any object that tries into a gravitational singularity. This connection between information theory and relativity reveals something profound about the nature of reality. Information isn't just an abstract concept, it's a physical quantity that obeys conservation laws and thermodynamic principles. The speed of light represents not just a limit on the motion of matter and energy, but also a limit on the propagation of information itself. Consider what happens when you try to send information faster than light. In our universe, all information transfer requires some physical process, the movement of particles, the propagation of waves, or the change of quantum states. But all of these physical processes are limited by the speed of light. There's simply no way to transfer information from one location to another without using some physical mechanism that respects Einstein's speed limit. This has profound implications for any hypothetical faster-than-light communication system. Even if we could somehow bypass the energy requirements for accelerating matter to light speed, we still couldn't send information faster than light without violating the fundamental principles of information theory. The relationship between energy and information also creates additional barriers to light speed travel. According to Landauer's principle, erasing information requires a minimum amount of energy equal to kT ln 2, where K is Boltzmann's constant and T is the temperature. This might seem like a tiny amount of energy, but it becomes significant when dealing with the enormous information content of macroscopic objects. Every atom in your body contains multiple bits of information about its quantum state. A typical human body contains about 7 times 10 to the 27 atoms, each storing multiple bits of information. As you accelerate toward light speed, relativistic effects would scramble this information, requiring enormous amounts of energy to maintain the complex molecular structures that define your existence. The process of acceleration itself requires constant information processing. Your body must continuously adjust to changing reference frames, maintaining the delicate balance of chemical reactions and biological processes that keep you alive. But as you approach light speed, time dilation makes this information processing increasingly difficult. From your perspective inside the accelerating spacecraft, time flows normally. But from the perspective of the outside universe, your biological processes slow down dramatically. The chemical reactions in your cells, the electrical signals in your nervous system, and the quantum processes that maintain your molecular structure all appear to slow to a crawl. This creates a fundamental mismatch between the rate at which your body can process information and the rate at which the external universe changes. Long before you could reach light speed, this mismatch would become so severe that your biological systems would be unable to function properly. The quantum mechanical aspects of information processing create additional barriers. Every quantum system has a finite information processing capacity, determined by its energy and the fundamental constants of nature. As you approach light speed, the energy of your constituent particles grows without bound, but their information processing capacity doesn't grow proportionally. This creates what physicists call the information bottleneck problem. The amount of information that needs to be processed to maintain a coherent quantum state grows faster than the system's ability to process that information. Eventually, the system becomes overwhelmed and loses coherence, effectively disintegrating at the quantum level. The holographic principle, derived from black hole thermodynamics, provides another perspective on these information-theoretic barriers. This principle suggests that all the information contained in a volume of space can be encoded on its boundary surface. This has profound implications for objects approaching light speed. As length contraction compresses an object in the direction of motion, the ratio of its volume to its surface area changes dramatically. At some point, the object's information content would exceed what could be encoded on its boundary surface, violating the holographic principle. This represents yet another fundamental barrier to light-speed travel. The concept of computational complexity also plays a role. Maintaining the quantum coherence of a macroscopic object requires solving computational problems that become exponentially more difficult as the system size increases. For an object approaching light speed, the computational requirements for maintaining coherence would exceed the computational capacity of the universe itself. These information-theoretic barriers reveal that the speed of light isn't just a limit on motion, it's a limit on the complexity and organization that can exist in our universe. The light-speed barrier ensures that information, energy, and entropy remain properly balanced, preventing the formation of structures that would violate the fundamental principles of physics. The connection between thermodynamics and relativity also explains why the universe has a maximum temperature, known as the Planck temperature. At this temperature, approximately 10 to the 32 Kelvin, thermal energy becomes so intense that it would create black holes spontaneously. This temperature represents the point where thermodynamics and general relativity merge into a unified description of reality. Objects approaching light speed would experience enormous thermal stresses due to their kinetic energy. Long before reaching light speed, these thermal effects would exceed the Planck temperature, causing the object to collapse into a black hole or disintegrate into fundamental particles. The universe's thermal limits provide yet another barrier to light-speed travel. The arrow of time, which emerges from the second law of thermodynamics, also plays a crucial role. As entropy increases, it defines a preferred direction for the flow of time. But for an object traveling at light speed, time dilation becomes infinite, effectively stopping the flow of time altogether. This would freeze the increase of entropy, violating the second law of thermodynamics. The universe prevents this violation by making light-speed travel impossible for massive objects. Only massless particles like photons can travel at light speed, and they don't experience the passage of time in the same way that massive objects do. For photons, the concept of entropy increase doesn't apply in the usual sense. When we look out into the vast cosmos, we find overwhelming evidence that the light-speed barrier is absolute across the entire observable universe. From the behavior of distant galaxies to the echoes of the Big Bang itself, every astronomical observation confirms that nothing with mass has ever exceeded the cosmic speed limit, not even in the most extreme environments imaginable. Let's start with one of the most spectacular confirmations, the observation of supernova 1987A in the Large Magellanic Cloud. This stellar explosion occurred about 168,000 light-years from Earth, and it provided a unique opportunity to test the universality of light speed across cosmic distances. When the star exploded, it released both photons and neutrinos. Neutrinos are nearly massless particles that barely interact with matter, allowing them to escape the collapsing star's core immediately. The photons, traveling at light speed, had to fight their way through the star's outer layers before beginning their journey to Earth. Despite this head start, the neutrinos arrived only about 3 hours before the light, exactly what we'd expect given the time it takes light to escape from a collapsing stellar core. If neutrinos could travel faster than light, they should have arrived years earlier. Instead, their near-simultaneous arrival confirmed that even these ghostly particles respect Einstein's speed limit. The Kamiokande 2 detector in Japan and the IMB detector in Ohio both recorded the neutrino burst from this supernova. The timing of these detections, combined with optical observations of the explosion, provided one of the most precise tests of relativistic physics across intergalactic distances. The results matched theoretical predictions to extraordinary precision. But supernovae aren't the only cosmic laboratories testing the light-speed barrier. Active galactic nuclei, the supermassive black holes at the centers of some galaxies, create jets of matter that shoot out at incredible speeds. These jets can extend for millions of light years and contain particles accelerated to 99.9% light speed or higher. The Very Long Baseline Array and other radio telescope networks have tracked these jets for decades, measuring their apparent motion across the sky. In some cases, the jets appear to move faster than light, a phenomenon called superluminal motion. But this is actually an optical illusion caused by the jets moving almost directly toward us at near-light speeds. When astronomers account for projection effects and time delays, they find that the actual speeds of these jets never exceed light speed. Even when powered by black holes millions of times more massive than our Sun, with magnetic fields strong enough to tear atoms apart, these cosmic accelerators cannot push matter beyond Einstein's limit. Gamma-ray bursts provide another extreme test. These are the most energetic explosions in the universe since the Big Bang, releasing more energy in seconds than our Sun will produce in its entire lifetime. The particles accelerated by these explosions carry energies that dwarf anything we can produce on Earth. The Fermi Gamma-Ray Space Telescope has observed hundreds of these bursts, measuring the arrival times of photons with different energies. If the speed of light varied with energy, if higher energy photons traveled faster, we would see high-energy gamma rays arriving before lower energy ones. But observations show that all photons, regardless of energy, travel at exactly the same speed across billions of light years. One particularly striking example is GRB 090510, a gamma-ray burst that occurred when the universe was less than 1 billion years old. Despite traveling for over 12 billion years to reach us, the high-energy and low-energy photons arrived within milliseconds of each other. This places incredibly tight constraints on any possible variation in light speed, less than 1 part in 10 to the 17. The cosmic microwave background radiation provides evidence on the largest possible scales. This faint glow, the afterglow of the Big Bang, has been traveling through space for 13.8 billion years. The Planck satellite has mapped this radiation with exquisite precision, revealing tiny temperature fluctuations that encode information about the early universe. These fluctuations show patterns that depend critically on the speed of light being constant throughout cosmic history. If light speed had varied even slightly over billions of years, these patterns would be distorted in ways we don't observe. The cosmic microwave background serves as a fossil record confirming that light speed has remained constant since the universe was only 380,000 years old. Gravitational lensing provides another cosmic confirmation. When light from distant galaxies passes near massive objects, its path is bent by the curvature of spacetime. This creates multiple images of the same galaxy, with light taking different paths to reach us. By measuring the time delays between brightness variations in these multiple images, astronomers can test whether light traveling different paths maintains the same speed. The CosmogRail project and other gravitational lens monitoring programs have measured these time delays for dozens of lensed quasars. In every case, the delays match predictions based on light traveling at constant speed, regardless of the path taken or the gravitational fields encountered. Even when passing through the intense gravity near galaxy clusters, light maintains its cosmic speed limit. Pulsar timing provides some of the most precise tests of relativity in strong gravitational fields. Pulsars are rapidly rotating neutron stars that emit beams of radiation like cosmic lighthouses. Some pulsars spin hundreds of times per second with timing stability that rivals atomic clocks. The double pulsar system, PSRJ0737-3039, consists of two pulsars orbiting each other every 2.4 hours. This system allows astronomers to test relativity in conditions of extreme gravity and high orbital speeds. After decades of observations, every relativistic effect, from time dilation to gravitational wave emission, matches Einstein's predictions perfectly. The pulsar's orbital decay due to gravitational wave emission has been measured to better than 0.1% precision. This wouldn't be possible if the speed of light or gravity varied even slightly from Einstein's predictions. The system serves as a natural laboratory, confirming that relativistic effects work exactly as expected, even in the most extreme environments. Fast radio bursts, discovered in 2007, provide a new tool for testing cosmic speed limits. These millisecond duration radio pulses come from distant galaxies and carry information about the material they pass through on their journey to Earth. The dispersion of these signals, how different frequencies arrive at slightly different times, depends on the density of electrons along the path. By measuring this dispersion, astronomers can test whether radio waves of different frequencies travel at the same speed across cosmic distances. The results consistently show that all electromagnetic radiation, regardless of wavelength, travels at exactly light speed. Even after journeying billions of light years through intergalactic space, these signals respect Einstein's speed limit. The expansion of the universe itself provides a fascinating perspective on the light-speed barrier. While galaxies cannot move through space faster than light, space itself can expand at any rate. During cosmic inflation in the early universe, space expanded much faster than light speed, carrying galaxies apart at superluminal velocities. But this doesn't violate relativity because the galaxies aren't moving through space. Space itself is expanding between them. This distinction is crucial. The light speed limit applies to motion through space, not to the expansion of space itself. This is why we can observe galaxies whose light has traveled for billions of years, even though they're now much farther away than light could have traveled in that time. Type Ia supernovae, used as standard candles to measure cosmic distances, provide additional evidence. These explosions have consistent peak brightness, allowing astronomers to determine how far away they are. By comparing their distances with their redshifts, we can map the expansion history of the universe. These observations, which earned the 2011 Nobel Prize in Physics, revealed that the universe's expansion is accelerating, but they also confirmed that light from these distant explosions travels at constant speed, regardless of the expansion of space or the presence of dark energy. The light-speed barrier remains absolute even as the universe itself evolves. The search for cosmic strings, hypothetical, one-dimensional defects in space-time, has also confirmed relativistic limits. If cosmic strings exist, they would create distinctive gravitational lensing patterns and gravitational wave signatures. But any signals from cosmic strings would still propagate at light speed, unable to exceed the cosmic limit even when generated by these exotic objects. Observations of galaxy clusters, the largest gravitationally bound structures in the universe, provide evidence on the grandest scales. When galaxy clusters collide, we can observe the behavior of different components, stars, gas, and dark matter, as they interact. The Bullet cluster, where two clusters collided about 3.7 billion years ago, shows that even in these titanic collisions, nothing exceeds light speed. Throughout history, brilliant minds have proposed clever ways to circumvent the light speed barrier. From wormholes to warp drives, from tachyons to quantum entanglement, these ideas capture our imagination and fuel science fiction. But when we examine them closely through the lens of rigorous physics, we find that the universe has closed every loophole, maintaining its cosmic speed limit with ironclad consistency. Let's start with wormholes, perhaps the most famous proposed shortcut through space-time. A wormhole is a theoretical tunnel connecting distant regions of space, potentially allowing travel between them without crossing the intervening distance. Think of it like poking a hole through a folded piece of paper instead of traveling along its surface. The mathematics of general relativity does allow for wormhole solutions, first discovered by Einstein and Nathan Rosen in 1935. These Einstein-Rosen bridges appear naturally in the equations describing black holes. But there's a crucial catch. These wormholes are unstable and collapse faster than light could traverse them. To keep a wormhole open long enough for anything to pass through, you would need exotic matter with negative energy density. This isn't just rare or difficult to produce, it violates fundamental principles of physics. The averaged null energy condition, a cornerstone of general relativity, states that the average energy density measured by any light ray must be non-negative. While quantum mechanics allows for tiny, temporary violations of this condition through quantum fluctuations, creating a macroscopic wormhole would require massive, sustained violations that appear to be impossible. Every attempt to design a traversable wormhole runs into this fundamental barrier. The universe seems to protect its speed limit by making shortcuts physically impossible. The Alcubierre warp drive, proposed in 1994, takes a different approach. Instead of creating a shortcut, it would contract space in front of a spacecraft and expand it behind, creating a warp bubble that carries the ship faster than light. Technically, the ship never exceeds light speed in its local reference frame. It's space itself that's moving. This sounds promising, but the energy requirements are staggering. Initial calculations suggested that creating a warp bubble would require more energy than the entire observable universe contains. Later refinements reduced this to merely the energy equivalent of Jupiter's mass, but that's still impossibly large. More fundamentally, the warp drive requires the same exotic matter with negative energy density as wormholes. It also creates closed time-like curves, paths through space-time that loop back to their own past. This would allow time travel and create causality paradoxes, suggesting that the universe's consistency protection mechanisms would prevent warp drives from functioning. Recent research has shown additional problems with warp drives. The boundary of the warp bubble would accumulate enormous energies, creating a blast of radiation that would destroy anything at the destination. The interior of the bubble would also be causally disconnected from the exterior, making it impossible to control or steer the drive once activated. Tachyons, hypothetical particles that always travel faster than light, represent another attempt to bypass Einstein's limit. The mathematics of special relativity doesn't explicitly forbid faster-than-light particles as long as they never slow down to light speed. Just as massive particles can't accelerate to light speed, tachyons couldn't decelerate to it. But tachyons create immediate paradoxes. They would have imaginary mass, meaning their mass squared would be negative. They would also travel backward in time from some reference frames, allowing information to be sent into the past. This would violate causality and create grandfather paradox scenarios where you could prevent your own existence. Extensive searches for tachyons have found no evidence for their existence. Particle physics experiments, cosmic ray observations, and astronomical surveys have all come up empty. The theoretical problems combined with the complete lack of observational evidence suggest that tachyons are mathematical curiosities rather than physical realities. Quantum entanglement often gets misrepresented as a way to communicate faster than light. When two particles are entangled, measuring one instantly affects the other, regardless of the distance between them. Einstein called this spooky action at a distance, and it seems to violate the light speed limit. But quantum entanglement can't actually transmit information faster than light. The measurement results are random. You can't control what value you'll measure. While the correlations between entangled particles are established instantly, extracting useful information from these correlations requires comparing measurements, which can only be done through classical communication channels limited by light speed. The no-communication theorem in quantum mechanics proves rigorously that entanglement alone cannot transmit information. Every proposed scheme for faster-than-light communication using quantum effects has been shown to fail when analyzed carefully. The universe maintains its speed limit even in the quantum realm. Some theories propose that space-time might be discrete rather than continuous at the smallest scales. In these theories, space consists of indivisible units, like pixels on a screen. Some researchers hoped this might allow for instantaneous jumps between adjacent pixels, bypassing the light speed limit. But detailed analysis shows that discrete space-time models still respect causality and the light speed limit. Information and matter can only propagate through the discrete structure at speeds up to and including light speed. The discreteness might change physics at the Planck scale, but it doesn't provide a loophole for faster-than-light travel. Extra dimensions proposed by string theory and other unified theories offer another potential avenue. If our universe has hidden spatial dimensions, perhaps we could take shortcuts through them, like an ant crawling across a cylinder instead of around it. However, these extra dimensions must be either extremely small, compactified, or our matter must be confined to a lower dimensional brane within the higher dimensional space. In either case, the light speed limit applies within whatever dimensions we can access. The existence of extra dimensions doesn't change the fundamental speed limit. It just applies that limit in a higher dimensional context. Variable speed of light theories propose that the speed of light might have been different in the early universe, or might vary in different regions of space. These theories attempt to solve certain cosmological puzzles without invoking inflation, but observations place incredibly tight constraints on any variation in light speed. As we've seen from gamma-ray bursts and other astronomical observations, light speed is constant to better than 1 part in 10 to the 17. Any variation would also change other fundamental constants, affecting nuclear physics and chemistry in ways we don't observe. Some researchers have proposed that dark energy or dark matter might provide a way around the light speed barrier. Perhaps these mysterious components of our universe follow different rules than ordinary matter and energy, but all evidence suggests that dark matter and dark energy still respect Einstein's speed limit. Dark matter appears to be made of particles that interact gravitationally but not electromagnetically, while dark energy seems to be a property of space itself. Neither provides a mechanism for faster-than-light travel. Analog models of gravity, where flowing fluids mimic the behavior of curved space-time, have led some to speculate about breaking the sound barrier in these systems as an analog to breaking the light barrier. But these analogies have fundamental limitations. The speed of sound in a fluid is not a fundamental limit like the speed of light in space-time. The holographic principle, which suggests that our three-dimensional universe might be encoded on a two-dimensional surface, has sparked speculation about bypassing three-dimensional speed limits. But the holographic principle is about information encoding, not about creating shortcuts. The same speed limits apply whether we think of physics in 3 dimensions or in the holographic description. Even the most exotic proposals from the fringes of theoretical physics respect the light speed limit. Whether it's loop quantum gravity, causal set theory, or emergent space-time models, every serious attempt to describe fundamental physics maintains causality and prevents faster-than-light signaling. The consistent failure of all attempts to find loopholes in the light-speed barrier tells us something profound. This isn't just a technological limitation or a consequence of our current understanding. The speed of light limit appears to be woven into the deepest fabric of reality, protected by multiple independent mechanisms that ensure its inviolability. Every new discovery in physics, from quantum mechanics to general relativity to quantum field theory, has only reinforced the absolute nature of this cosmic speed limit. The universe seems to be constructed in a way that makes faster-than-light travel not just difficult or impractical, but fundamentally impossible. The light speed barrier means that the universe is far lonelier than science fiction would have us believe. Even our nearest stellar neighbor, Proxima Centauri, lies 4.24 light-years away. A journey there at 99% light speed would take over 4 years from the traveler's perspective, and much longer from Earth's viewpoint. The vast majority of stars in our galaxy are hundreds or thousands of light-years distant, placing them centuries or millennia away, even at near-light speeds. This cosmic isolation has profound implications for the search for extraterrestrial intelligence. If alien civilizations exist, they face the same light speed barrier we do. There can be no galactic empires with faster-than-light communication, no cosmic internet connecting distant worlds in real time. Each civilization is fundamentally isolated by the vast distances and finite speed of light. But this limitation also protects us. Any hostile alien civilization would face the same constraints, unable to launch surprise attacks or rapidly expand across the galaxy. The light speed limit acts as a cosmic quarantine, keeping civilizations separated and preventing any single species from dominating the galaxy through superior technology or aggression. The impossibility of faster-than-light travel also shapes how we must think about humanity's future. If we're to spread beyond Earth, it won't be through quick jaunts between stars. Instead, we'll need generation ships, vast arcs carrying entire communities on journeys lasting centuries or millennia. Or we might send robotic probes with artificial intelligence, patient explorers that don't mind the long travel times. Time dilation offers a strange consolation. While centuries might pass on Earth, travelers approaching light speed would experience much shorter journeys. At 99.9% light speed, a journey to the galactic center, 26,000 light-years away, would take only about 1,200 years from the traveler's perspective. Still a long time, but not impossibly so for a civilization thinking on cosmic timescales. This creates a poignant scenario for future star travelers. They could journey to distant stars and return to Earth, but everyone they knew would be long dead, their civilization transformed beyond recognition. The light speed barrier doesn't just separate us in space, it creates unbridgeable gulfs in time. The energy requirements for near-light speed travel force us to think on astronomical scales. To accelerate even a modest spacecraft to 90% light speed would require energy infrastructure far beyond anything we can currently imagine. We might need to harness entire stars, building Dyson spheres to capture their total energy output. The light speed barrier doesn't make interstellar travel impossible, but it demands that we become a fundamentally different kind of civilization to achieve it. These limitations might explain the Fermi paradox, the puzzling absence of obvious alien civilizations despite the vast number of potentially habitable planets. Perhaps intelligent life is common, but the light speed barrier keeps civilizations confined to their local stellar neighborhoods. The galaxy might be teeming with life, but each pocket of intelligence is isolated by the vast distances and fundamental speed limits. The light speed barrier also has profound philosophical implications for free will and determinism. Because information cannot travel faster than light, the future light cone from any event defines the absolute limit of its possible influence. This creates a kind of cosmic determinism, not in the sense that the future is predetermined, but in the sense that causal influences are strictly limited by the geometry of space-time. Yet within these constraints, incredible complexity and beauty emerge. The same laws that prevent faster-than-light travel also enable the stable existence of atoms, molecules, and life itself. The light speed limit is part of a finely tuned set of physical laws that allow for the emergence of complexity and consciousness in the universe. The impossibility of faster-than-light travel also deepens our appreciation for the preciousness of Earth. We can't easily escape to other worlds if we damage this one. The cosmic speed limit makes Earth not just our home, but potentially our only home for centuries or millennia to come. This should inspire us to be better stewards of our planet, knowing that the stars, while not forever out of reach, are far more distant than our dreams might wish. But perhaps the most profound implication is how the light speed barrier connects us to the cosmos. When we look at the night sky, we're seeing the universe as it was, not as it is. The light from distant stars and galaxies has traveled for years, centuries, or billions of years to reach us. We're connected to the cosmos through a web of light, each photon a messenger from the past, carrying information across the vast distances. This cosmic perspective transforms our understanding of our place in the universe. We're not separate from the cosmos. We're woven into its fabric through the constant exchange of light and information. Every atom in our bodies was forged in the hearts of stars, and the light from those ancient stellar furnaces still travels through space, carrying the story of our origins. The light speed barrier also reminds us of the importance of patience and long-term thinking. If humanity is to have a cosmic future, we must learn to think and plan on timescales far longer than our current political and economic systems encourage. Interstellar travel will require multi-generational commitments and civilizational stability over centuries. This might ultimately be a gift. The impossibility of quick fixes or easy escapes forces us to confront our challenges here and now. We can't run away to the stars when things get difficult on Earth. We must solve our problems, learn to live sustainably, and create a civilization capable of thinking and acting on cosmic timescales. The scientific journey we've taken, from Einstein's insights to quantum mechanics, from particle accelerators to astronomical observations, reveals something beautiful about the nature of scientific truth. The light speed barrier isn't just a human invention or a temporary limitation of our technology. It's a fundamental truth about reality that we've discovered through careful observation and rigorous thinking. This discovery connects us to any other intelligent beings in the universe. Whatever their biology, culture, or technology, they must have discovered the same truth. The speed of light is a universal constant that all civilizations must recognize and respect. In this way, science provides a truly universal language, a set of truths that transcend species and cultures. As we stand at the threshold of becoming a spacefaring civilization, the light speed barrier challenges us to be creative, patient, and wise. We might never build warp drives or jump through wormholes, but we can still reach for the stars. It will just take longer than we might wish, require more energy than we might hope, and demand more patience than we might naturally possess. But perhaps that's the point. The universe's speed limit forces us to grow up as a species, to think beyond our individual lifespans, and to work together on projects that benefit future generations rather than ourselves. The impossibility of faster-than-light travel might be the universe's way of ensuring that only mature, patient, and wise civilizations can spread among the stars. In the end, the light speed barrier isn't a wall that confines us. It's a fundamental feature of the cosmos that shapes our destiny. It connects us to the universe through the constant flow of light, protects us from cosmic dangers, and challenges us to become something greater than we are. The stars are not forever out of reach, but the journey to them will transform us in ways we can barely imagine. As you look up at the night sky, remember that you're seeing the universe through the lens of light speed limits. Every star you see is showing you its past, every galaxy a glimpse of cosmic history. We are all time travelers, moving into the future at the rate of 1 second per second, connected to the cosmos by the endless dance of light across the void. The impossibility of faster-than-light travel is not a limitation to mourn, but a truth to embrace. It makes the universe comprehensible, maintains the order of cause and effect, and ensures that our cosmic journey will be one of patience, wisdom, and wonder. We will never break the light speed barrier, but in understanding why, we've gained something far more valuable, a deep appreciation for the elegant and beautiful way our universe works. The cosmic speed limit is absolute, unbreakable, and eternal. And in accepting this truth, we take our first real step toward becoming a truly cosmic civilization, one that works with the laws of nature rather than against them, one that finds wonder in the journey rather than just the destination. The stars await, patient and eternal, and though the journey will be long, it will be humanity's greatest adventure. If you are still watching, make sure to hit that like and subscribe to the channel. And if you enjoyed this video, I am sure you're gonna love this other one at the left side of the screen. 54 things that shouldn't exist in space, but do. In this video, discover 54 mind-blowing space discoveries that defy the laws of physics and challenge everything we thought we knew about reality. From planets that rain glass sideways, stars older than the universe, diamond worlds, and much more. See you there.